Welcome back to another explainer. This is where we take those everyday things you see all the time and we'll turn them into totally fascinating science. Today, we're unpacking something you've probably seen 100 times, but honestly, you might never have thought about how it actually works mechanically. We're going on a journey, starting from super simple macro observations all the way down to the invisible molecular mechanics that make our physical world tick. So get ready, because today we're exploring the thermal expansion of liquids.
Okay, let's dive right into this. Have you ever noticed the liquid in a thermometer just kind of shooting up when you put it in hot water? Or, hey, maybe you've left a completely full water bottle out in the baking sun, and suddenly it looks like it's swelling up, like it's just ready to burst. Why exactly does this happen? I mean, it almost seems like magic, right? Like the liquid is somehow multiplying in real time. But it's actually a very specific, incredibly predictable mechanical process. Section 1. The Thermometer Mystery. Solving the Puzzle. And right here is our anchor for today's entire explainer. Thermal expansion is simply the increase in the volume of a liquid when its temperature increases. That's the golden rule we're working with today, guys. When the heat goes up, the physical space that the liquid takes up, that goes up too. It's direct, it's proportional. But, just reading a definition isn't really enough to grasp it. We need to know why this actually happens. Which brings us to Section 2. What is expansion? Under the microscope. When we break this whole thing down into a step-by-step chain reaction, it always starts with heat being applied. And heat at its core is just energy. So as that energy enters the liquid, the molecules start moving way faster. Think of it like a crowded, kind of slowly swaying dance floor, right? When a fast, upbeat song comes on, that's the heat being introduced. People start dancing faster, swinging their arms, moving around a lot more. And what naturally happens next? Well, they have to spread farther apart so they don't bump into each other. Finally, because every single molecule is now spread out, the entire crowd, or in our case, the liquid itself, literally occupies more physical space, meaning the total volume increases. It's this brilliantly simple invisible dance happening all around us. So, the absolutely crucial point here is contrasting this behavior with solids. Unlike solids, which can expand in length, width, and height while keeping their general rigid structure intact, liquids have absolutely no fixed shape. They just kind of lazily take the shape of whatever container they're sitting in. Because they're formless like that, when they heat up, they expand only in volume. The molecules just push outward in every possible direction, taking up more and more room inside whatever vessel is holding them. Section 3. The plot twist. Real versus apparent. Now, this is where it gets super interesting because it brilliantly illustrates the difference between what's really happening and what we merely think we see. Real expansion is the actual true mathematical increase in the liquid's volume because of the heat. But on the flip side, we have apparent expansion. Think about it. When you heat a liquid, say in a glass beaker over a flame, the liquid isn't the only thing getting hot. The glass container is absorbing that heat too, which means the solid container itself is also expanding. So, because the container has actually grown slightly larger, the liquid level doesn't seem to have risen as much as it actually did. The observed expansion, that's the apparent expansion, is slightly less than the real expansion. It's kind of like an amazing optical illusion, but it's created entirely by the physics of the container expanding right alongside the liquid inside it. Section 4. Applications. Everyday engineering. Let's zoom back out to the real world, because engineers constantly have to solve for the reality of thermal expansion. First on the list, mercury and alcohol thermometers. Like we mentioned at the start, they don't just tolerate this expansion, their entire function literally relies on capturing it inside a measured glass tube. But consider some other everyday examples. Vehicle radiators, they are specifically designed not to be filled completely to the top. Why? Well, because the running engine is going to heat that coolant, causing it to rapidly expand. If the radiator was completely full, the pressure would literally crack it open. The exact same logic applies to the fuel tanks in your car. Engineers intentionally leave empty space at the top so that when your car is parked in the blazing sun, the expanding fuel has somewhere to go without rupturing the gas tank. And on a massive scale, industrial storage tanks are heavily engineered with expansion joints and safety vents to allow thousands of gallons of potentially dangerous liquids to expand safely. I mean, those tiny, invisible dancing molecules, they can generate enough collective force to burst thick steel if we don't engineer space for them. Crazy, right? Section 5. The big takeaway. Essential concepts. Okay, so here is exactly what you need to lock in from this explainer. Number 1, Heat increases a liquid's volume purely because the molecules get energized and start moving farther apart from one another. Number two, we always have to account for both real and apparent expansion, because the actual real-world containers holding our liquids are expanding when they're heated too. And finally, understanding these invisible mechanics isn't just, fun academic trivia, it's absolutely crucial science. It dictates the structural safety of our everyday equipment and massive industrial designs. So I'm going to leave you with this final thought. Next time you walk past a giant industrial fuel tank, or check your car's radiator, or even just read a thermometer to see if you have a fever, ask yourself, what invisible molecular mechanics are happening right in front of me? Our world is absolutely full of these hidden dances of physics, and they are constantly shaping our reality in ways we rarely take the time to appreciate. So keep asking those questions, keep visualizing the mechanics, and thank you so much for joining me for today's Explainer.